Hello, everyone. My name is Apostolos, and I'm going to present you our work on estimating the filling level of containers using data augmentation. This work is in collaboration with my colleagues from Queen Mary University London and EPFL. Deep learning has achieved impressive results in multiple tasks, like image classification, mainly due to the availability of huge amounts of training data. However, in many real-world applications, we only have access to limited amount of training data, and hence deep learning does not always perform the desired way. For dealing with the absence of data, one of the most common techniques is to use transfer learning. With transfer learning, one trains a neural network on a very big dataset, like ImageNet, and then fine-tunes the parameters of the network using data from the actual task of interest. However, one obscure property of transfer learning is that there is no explicit guarantee that the transferred features are actually relevant for the target task. An alternative for dealing with the absence of data is to artificially increase the training set through data augmentation. In this setting, the idea is to train the network on a dataset that has been augmented with transformed versions of the original data. Nevertheless, the main difficulty of data augmentation is to ensure that the transformed samples are actually representative of the data that appear at test time. Examples of scarce training data can be found in applications of robot perception, where the goal is to infer the world using only a few available observations. And as a use case, one can think of a daily task where humans and robots have to perform handovers of objects, such as containers and drinking glasses. For this task to be safely and accurately executed, an important property that needs to be estimated is the weight of the container. And for doing so, the robot should estimate both the volume of the container and the amount of content within the container. In fact, this simple scenario is actually very challenging, especially if the perception is based only on vision through standard RGB images. And the problem becomes even more difficult if we consider the distribution shifts that can occur during test time. For instance, we might come across images with containers of different shape, transparency, or occlusions than those observed during training. Hence, we need to ensure that the predictions of our system remain robust even when such differences occur at test time. If we have a look on the prior works for estimating the filling level using only RGB information, we will notice that transfer learning is the most commonly used technique, either by directly training a network on ImageNet and then fine-tuning it on the target task, or by adversarially training a network on ImageNet before performing fine-tuning. In fact, this approach has been shown to further increase the performance of standard transfer learning. But recall that in transfer learning, there is no mechanism to explicitly guarantee that the transferred features are actually relevant for the target task. Hence, in this work, we question the necessity of transfer learning. Instead, we investigate if we can design a data augmentation scheme that can explicitly capture the test time data variability in the task of filling level estimation. First of all, let's see our data. We will work on the CCCM dataset since it offers a large variability in terms of container shape and transparency. CCCM consists of roughly 10,000 RGB images of cups and drinking glasses. The containers can be empty, half full, full, or unknown, where the unknown class corresponds to cases where the filling level cannot be estimated through direct vision, for instance, for opaque containers. Finally, the containers can be filled with water, pasta, or rice. In the official release of CCCM, the authors also propose 3 different dataset splits, such that at test time, there will always be some container with unseen properties. In the first split, the test set contains a champagne flute and a cocktail glass, which have a very unique shape with respect to any container in the training set. In the second split, all the test set containers have a stem, which is totally absent from the training set. Finally, in the third split, there are 2 colored containers in the test set, while no color information is available in the training set. But let's have a closer look. It seems that for the first and the second split, the differences between the training and the test data are mostly shape related. Hence, if one would want to transform the training data such that they resemble the ones appearing at test time, then one should seek for a transformation that deforms different parts of the training containers. While if we look at the third split, we will notice that the main differences are related to the color and the spatial frequencies of the containers. Hence, in general, we should be looking for transformations that can efficiently alter the shape, color, and spectral content of an object. To this end, it is reasonable to focus on the recently proposed prime augmentation algorithm. And this is because prime can generate quite diverse augmentations by just using three simple yet very rich transformation families that follow a max-entropy distribution. And these transformations specifically operate on the spatial, color, and spectral domain of the image, which align well with the test time differences we described for the three dataset splits. Now, let's see how prime takes as input an image X and transforms it into an image XT. For a given image X, prime composes a series of m randomly drawn transformations and applies them on X. For example, a spatial transform followed by another spatial transform and finally by a color transform. Then this process is repeated n times, and the final transformed image XT is synthesized as the linear combination of all the composition outputs. Finally, the image that will be fed into the network is a linear interpolation between the original and the transformed image, where the coefficients of the interpolation are drawn from a beta distribution. Note here that the parameters of the beta distribution essentially determine if the pixels of the final image will contain information mostly from the clean or from the transformed image. By visualizing some examples generated with prime, we observe that indeed the transformed samples contain cups and glasses of high variability in terms of shape, color, texture, and illumination. But how much importance do we assign to these transformed samples with respect to the clean images? To answer this, we must focus on the mixing parameters. Recall that the parameters of the beta distribution control the pixel importance. Hence, we can try different parameters for the beta distribution, train a network on the resulting augmentations, and measure the performance of the network on the three dataset splits. By doing so, and based on these heat maps, we can see that the highest accuracy on each dataset split is consistently obtained when alpha is larger than beta, hence, when more importance is given to the transformed pixels. In other words, the test time distribution shifts are quite strong, and we must introduce a lot of information from the transformed samples in order for our network to generalize properly. And now that we have specified the desired parameters for our augmentations, let's thoroughly evaluate our method on the CCCM dataset. Regarding the different training strategies, we will train the network directly on CCCM, as well as using transfer learning and adversarial training combined with transfer learning. Note that the latter is the current state of the art on CCCM. Then we will train the network directly on CCCM, but using our data augmentation scheme. And finally, we will combine the state of the art transfer learning approach with our data augmentation scheme on CCCM. For the first dataset split, the challenges are mostly related to the unique shape of the champagne flute and the cocktail glass in the test set. We can see that transfer learning has a significant effect mostly on the case of the champagne flute, where training directly on CCM results into very low performance. However, by introducing our augmentation scheme, we can see that we improve the accuracy on every container, while the performance of our method is similar or better than the one of transfer learning. For the second dataset split, the challenges again are mostly related to the unique shape of the champagne flute and the cocktail glass, but also to the absence of any container with a stem in the training set. We can see that transfer learning has a significant effect both on the champagne flute and the cocktail glass when compared to standard training. By introducing our augmentation scheme, again, we can see that the accuracy on every container is improved, while the performance of our method matches or exceeds the one of transfer learning. Finally, in the third dataset split, the challenges are now related to the color and the spectral properties of the test time containers. We can see that transfer learning has a very powerful effect, especially on the red cap, where standard training achieves almost 0%, since 99% of the predictions assign the label full. With our augmentation scheme, we can see that the performance on the red cap is very close to transfer learning, but still slightly lower. However, on the rest of the containers, we observe that again, our augmentations can match or surpass the performance of transfer learning. Overall, we can say that for the task of filling level estimation, transfer learning might not be necessary since one can achieve similar or better performance by simply using our principal data augmentation scheme. To conclude, we focus on the problem of estimating the filling level, where the absence of training data along with the test time distribution shifts make it a challenging problem. And we investigated the impact of data augmentation. In this sense, we introduced a principal data augmentation scheme that uses spatial, color, and spectral transformations to synthesize images of high variability. Through experimental evaluations, we demonstrated that our method consistently achieves similar or better performance than transfer learning, hence avoiding the need of networks pre-trained on huge and potentially relevant datasets. Finally, and as a next step, we will incorporate in our scheme new transformations that can cover other types of test time distribution sets. Thank you very much for watching.